Hi guys. Today we're looking at the Chi Squared test. Specifically, there's three different Chi Squared tests. We're going to look specifically at goodness of fit. So the goodness of fit or GOF test today. We're going to look at a bag of Skittles then and a bag of M&Ms to perform a Chi Squared test for examples. All right, so first off, what is Chi Squared? Well, it's like another hypothesis test. So it's another kind of way to do a hypothesis test. All right, so there will be like a null hypothesis, an alternative hypothesis, that sort of stuff. And the distribution, though, is not going to be normal. All right, so we'll have one categorical variable, or later on we might have two categorical variables, leading to multiple proportions. So it's like a two proportion test, but with sometimes 3 or 4 or 5 or whatever, however many proportions we want, where we expect certain outcomes and measure how close to the observed outcomes these certain outcomes are. So the way we measure it, or the way we actually calculate the chi squared value, which does have an actual value, and it is like the Greek letter. So this x, this is a Greek x, this is called the letter chi. So this is why we get chi squared from. So the chi squared value, and if you're curious, we never actually get the chi value, we just get chi squared value. It is the sum of the difference between the observed and the expected squared divided by the expected. All right, so from each term, each part, we'll get this observed value. We'll have an expected value. We'll subtract them. We'll square them. And then we'll divide by the expected. And we'll add up all those terms, because this means add. And that'll give us our chi squared. And then, so we'll talk about the chi squared distribution. So the chi squared distribution looks like this over here, or either one of these guys. It does depend on the degrees of freedom, which depends on the number of categories, not your sample size. So this is different. We'll get to that later. But it's always this distribution. It's always skewed to the right. All right, it starts at 0. It's so like it's at 0, 0. And then it goes up. It hits the high point somewhere here. Don't know what that is. Who knows? And then it comes back down, and it has this tail over here off to the right. And our p-value is the probability of being at the chi squared value that we get or beyond. All right, so it's kind of like normal CDF, and we're just looking at the tail on one side, but it's with chi squared. And if you're curious, there is a chi squared CDF on your calculator. It's under that same distribution menu, like second vars. Get you to that distribution menu, and then it is number 8 chi squared CDF, which we'll take a look at here in a second. Then it works kind of like the normal or a t-distribution. It has a lower bound, an upper bound, a degrees of freedom, which is your number of categories minus 1, and just enter, and that gives you your p-value. And then we treat it just like we did with hypothesis test with our p-value. All right, and I think that was me covering all this stuff here, and we do compare it to alpha at the end, so it does work just like a hypothesis test. All right, so here's how the chi squared goodness of fit test works and examples of when we would use it. So it's used to determine if the distribution of a categorical variable with 2 or more categories fits the expected results. All right, so in other words, we are working with one sample. So there's 3 different chi squared things, and you got to be able to tell them apart. So chi squared goodness of fit is one sample and one categorical variable. So do M&Ms match their given color distribution? All right, we take one sample, like one bag of M&Ms or 2 bags of M&Ms or whatever, and the one variable is color. All right, so one variable there. Like rolling a die repeated number of times, however many times you do it would be how many, your sample size. And getting like 1, 2, 3, 4, 5, and 6, how many times they got each one, we would think it would be 1/6 for each number. M&Ms actually tells you what the color distribution is if you look it up. It's online, it's available. But again, anyway, those are 2 examples of when we do chi squared test. Since it is a hypothesis test, we draw our little boxes, we draw our little cross, and we fill in our boxes, state, plan, do, conclude, just like before. State, we just have to have our 2 hypotheses. Our null hypothesis is always going to be that the distribution of whatever it is we're working with is the same as claimed. And the alternative is that the distribution is different from claimed. So claimed could mean that it's uniform, or it could mean that it's certain percentages of each thing. All right, but we can just say as claimed, and that's okay. All right, and then we state our alpha value. If they don't give you one, we're going to use 0.5, 0.05. Our plan, just like before, we state the name of our test. It's a chi squared goodness of fit test. We check our conditions. We need a random sample. The independence is still the same thing with the sample size, n needs to be less than 10% of the population. but the normal condition has now changed. All right, so the large counts condition is what we call it. And we need that each of the expected counts is greater than or equal to 5. And we'll go over how to calculate that. All right, the do part, so it's a chi-squared goodness of fit test. It's under the test menu on your calculator. So like we could go to stat and then go over to test. And it's like a ways down. Like I think it's like D or something like that, chi-squared goodness of fit test. And C is just the chi-squared test. So there's multiple ones. We want goodness of fit now. Once we do it, we write down our chi-squared value, we write down our p-value, we write down our degrees of freedom. We're probably going to have lists L1 and L2 involved here. One of these will be observed, the other one will be the expected, and so on. Or we can do it by hand, and we can work out this, and each individual value, each observed value gives its own contribution. All right, and your calculator actually gives you those contributions if you want. The number of categories is your degrees of freedom. So categories minus 1 degrees of freedom, not your sample size. That's the biggest mistake people make. Not n, number of categories minus 1. All right, and we can do the chi-squared CDF to get the p-value also instead of doing the calculator test if we want. All right, if p is low, reject the ho, same as before. So we write the same sentence since the p-value and so on, less than or greater than alpha, whatever. We reject the ho, we fail to reject the ho, and then we write a sentence about this in context. So we have evidence of the alternative, or we don't have evidence of the alternative. Here's our example. So here's a bag of M&Ms. I took a picture of it, I spread it out, and so we could easily count it. And here's the breakdown of what M&Ms are supposed to be color-wise. And our question is do the M&Ms from a random bag of M&Ms show evidence that M&Ms do not follow the company's listed percentages? All right, so what we need to do is we need to count. So brown, 13%, and we have the observed. So observed is 5. Yellow, we've got 5 also. Green, we got 15 observed. Let's see, red, we've got 10 observed. Blue, looks like 9 there. And orange looks like we've got 12. So now the question is, how many are in this bag? So 5 plus 10 is 15, plus another 5 is 20, 35, 47, is that 56? So now that we know that there are 56 in the bag, we can work backwards and we can get the expected value. So we need 13% of 56. So this would be 0.13 times 56. And this would be 0.14, and 0.14 times it, and 0.16 times it. So let's break out my calculator here. There it is. On 0.13 times 56. Now it's not going to be a whole number. That's okay. 7.28. I want to make sure I counted these right. So 5 plus 10 plus 5 plus 15 plus 12 plus 9. Just to make sure. Okay, 56. Yep. So that's 7.28. Then we've got 0.14 times 56. All right, and 0.16 times 56. All right, so we've got 7.28, 7.84. This is also going to be 7.84, and then the 0.16 was 8.96. And then we've got 20% and 24%. So 0.20 times 56 and 0.24 times 56. So this is actually one of the harder ones because we have these percentages. It gets easier if they have a uniform distribution, we can just divide. But this is what, 11.2 and 12.96? All right. So now let's go ahead and we fill in our table here. So our null hypothesis will be that the colors of M&Ms are distributed as claimed. The alternative is the colors of M&Ms are not distributed as claimed. All right, or you could say that one color is different. At least one color is different from what's claimed. That would also work. They didn't give us an alpha value, so let's go ahead and just pick 0.05. We're doing a chi-squared goodness of fit test. So we can abbreviate that GOF. So that's one of our 3 abbreviations. Remember, we got SRS for simple random sample, CLT for central limit theorem, and now GOF for goodness of fit. Those are the 3 abbreviations we can use. All right, we were given a random bag, so it's a random sample. That checks out. The large counts, these are the expected values. These are the counts, and they are all greater than 5. So all expected counts are greater than or equal to 5, and there they are up there, circled. You do have to show it somewhere on your paper and like draw a line or something to say that that's where your expected counts are. All right, and independence, our n here is 56, which is surely less than 10% of all M&Ms. So that checks out. All right, we could calculate this. All right, we could calculate the actual chi-squared, and we could say chi-squared is equal to the difference between these, observed minus expected, so 5 minus 7.28 squared over, let's see, was it expected or observed? I think it was over expected, right? Yep, over expected, expected on the bottom. So expected is the 7.28 plus, and then we have to keep going. It'd be 7, or actually it'd be 10 minus 7.84. It does not matter if you switch the order on these. The important part is just getting the right number on the bottom. Plus dot, 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 and then we can go to the last one. So dot, dot, dot means just keep going, following that same pattern. The last one would be, what is that, 12 and 9, so 9 minus 12.96 squared over the expected, so that's 12.96. All right, and that'll give us our chi-squared. And then we would use, let's see, our degrees of freedom here would be 1, 2, 3, 4, 5, 6 minus 1. 5. The number of categories we have. So each color is a category. So our degrees of freedom would be 5. And then once we get this answer, we could put this into the chi-squared CDF. The chi-squared would be the lower bound. So we could do it like this, chi-squared CDF. And we would get whatever this chi-squared is as our lower bound. Our upper bound would be something big. It could always be 1,000. It's fine. And our degrees of freedom would be 5. And we could put that in. Or we could put these numbers into our calculator as lists. Like the one, we could put one of these in L1, like say the observed go in L1, the expected go in L2, and we could just go from there, and it would give us our chi-squared and our p-value. All right, so to the calculator either way. Let's do the list here. I think I have it doing it later, but let's just do it now. So we've got observed goes first. So we got 5, 10, 5, 15, 12, and 9. Next list, we've got, this one's going to be 7.28, and 7.84, another 7.84. The order does matter here, 8.96, so they need to match up 11.2 and 12.96. All right, so we do have the same number in each list. So now we're going to stat, over to test. We're looking for chi-squared GOF. There's chi-squared test. There it is, chi-squared goodness of fit. It is letter D. All right, let's see. Our observed, we put in list 1. So you do have to remember what you put in which list. Our expected, we're in list 2. Our degrees of freedom is 6 minus 1, so 5. And calculate. And there we go. So there's our chi-squared. There's our p-value. There's our degrees of freedom again. And if we want to, if we arrow over right away, it tells you the contribution from each value. So this would be the third one. This would be the contribution from yellow. There's the contribution from green, 4. That's probably the biggest one there. Contribution from orange. Gosh, that one's almost nothing because the numbers are close to each other. All right, and from blue, 1.2. So the biggest contribution came from the green. That was the biggest difference. All right, so our chi-squared is 7.67 or 7.68. Is that what that rounds to? And we need our p-value is 0.17. All right, so 0.17 is pretty normal size, like that's a good size p. So we say since the p-value equals 0.17 is greater than 0.05, which is what we chose for alpha, we fail to reject the null hypothesis. All right, I'm not going to write out what the null hypothesis is, but I'm going to write now context about the alternative. So we do not have significant evidence that the distribution or the color distribution of M&Ms is different from claimed. And there we go. All right, so that is how we do a chi-squared goodness of fit test. All right, so most of the time you can do all the calculations on your calculator, but sometimes they do want to see this work. If they say see the work, you really just have to show like one or two terms and then put plus ... and that's okay, and that's plenty. All right, so there it is on your calculator. We just saw me do it on your calculator, but it's there if you want to see it. All right, so now here's another one. I know we're running a little bit over on time today, but we'll try and make this quick. So Wrigley, the company that makes Skittles, claims that the colors of Skittles are evenly distributed. So they don't give us percents. They should have the same number of each, basically. Is there significant evidence that the colors of Skittles are not evenly distributed? Going right into it. So our null hypothesis, the colors of Skittles are evenly distributed. All right, that's the claim. So we're saying that's true. The alternative is the colors of Skittles are not evenly distributed. All right, so we could have at least one of them that's a lot bigger or one of them that's a lot smaller. We don't have any alpha given to us, so we'll use 0.05. There's lots of proportions here, so we're doing a chi-squared goodness of fit test. All right, this is a random bag of Skittles. In fact, any bag of Skittles I think I would take from the factory that's out for sale would be a random bag. All right, we're going to look at the expected counts in just a second here. We want them to be greater than or equal to 5, so we'll check on that here in a minute. And then for independence, let's see, our N is how many Skittles we have here. So let's see, we're going to need to know how many Skittles we have. So let's take a look at this. So we've got green, yellow, orange, red, and I'm going to call that purple. I know some of you like to call it brown. It's not brown, guys. It's purple. It's grape. All right, so I'm just going to make a little chart here. And I've got observed and then expected. All right, so we've got to put this somewhere so they can see it. So the green, we're just counting, we've got 12. Yellow, we've got 9. Orange, we've got, looks like 15. Red, looks like 13. And purple, that looks like 8 to me. If we add this all up, that gives us our N. So let's see, where's my trusty calculator? All right, don't need that anymore. So let's see, we've got 12 plus 9 plus 15 plus 13 plus 8. 9, 15, 13, 57. Oh, that's not a nice even number, is it? All right, and there's 5 colors, and there should be evenly distributed. So if we take 57 and divide it by 5, that would give us our expected for each one, 11.4. And luckily, 11.4 is greater than or equal to 5. All right, so all are 11.4, and they're all greater than or equal to 5. And look, I'm going to put an arrow here just so they don't get confused. My expected counts are all right there. I've shown them to you. They're there. I've labeled them expected. I've even drawn an arrow to them. All right, so you can't mess that up, right? AP graders have to be able to see that. 57 is definitely less than 10% of all Skittles. There's more than 570 Skittles on Earth. In fact, I think I've eaten more than 570 Skittles, not all at once. All right, and we're doing a chi-squared goodness of fit test on our calculator. And these are the two lists we're going to need. So let's go ahead and type those into lists. So stat, edit, and let's go over to L3. So we've got our observed are 12, 9, 15, 13, and 8. So we're one fewer category than last time. And 11.4 for each of these. Oh, left off a 1. All right, do try and keep track of what you've done with each one. Like on my paper, oftentimes I'll be like, okay, I know I put my observed in L3 and my expected in L4. They don't mind seeing that on your calculator or on your paper. That's okay. But you got to keep track of where you're putting what. So I like to just write it down on my paper. And let's see, goodness of fit tests. We're going all the way down to D. There we go, GOF. And we've got in L3 are now the observed. The expected are in L4. Our degrees of freedom, so we had 5 colors. So that's 5 minus 1 is 4 for our degrees of freedom. And calculate. And there's all the things we need to write down. Those first 3 things. All right, now before when I said we were doing tests, oftentimes we didn't get p-values over 0.5. Here, it's perfectly normal. All right, that's actually kind of like saying that this bag is kind of a normal bag. Like it's very expected. So our chi-squared is 2.9. I think it's 2.91. Our p-value was 0.57 if I remember right. And our degrees of freedom, we do need to write down, is 5 minus 1 is 4. We don't necessarily have to write 5 minus 1. We just need to write specifically that it is 4. And make sure I got that right, 0.57, yep. All right, so since our p-value equals 0.57, which is definitely bigger than 0.05, which is our alpha, we're going to fail to reject our null hypothesis. We do not have evidence. We do not have, I guess I should say, significant evidence that Skittles, I don't know why I put an R in there, are not uniformly distributed. All right, so as far as we know, this bag of Skittles is a perfectly regular bag, which is why we got this really big p-value and this pretty small chi-squared value. Usually we need chi-squareds like at 10 or 15 or 16 or 20 or something like that in order to reject. But again, it depends on your number of categories. All right, so that's it for this one. I'm sorry it's a little longer than normal, but it takes a long time to get through these examples and type everything into the calculator.